Because I remember you said keep on the gloves, so
Oh
I
yeah.
don't want to touch it with the gloves on my hands.
No, you're smart not to. That stuff can really hurt you. Even at low concentrations, that stuff can hurt you. Yeah. Oxidation reduction. Lose electrons, oxidize. Gain electrons, reduce. Yeah. YouTube. Live streaming. Go away. There we go. Copy. 1032. Where are you? Nope. 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 There it is.
Oh, off the wall?
No, it's something that we the notes school on November 10th only applies to session 1, 3, and 4 classes.
That includes us for session 1. That would include us for session 1.
Yeah, I'm saying that you guys you have session 2 classes.
Session 2's over.
Oh, that makes sense. So there are no classes on November 10th.
That's what I want to double check. No offense.
Yeah.
Before I announce it, because if I announce it and it's not true, I'm like, oh, I'm in trouble now.
What's on the academic calendar?
What's the date today? 27? 28. Thank you.
Yeah.
Okay. I'm going to send it to the boss.
Yeah. The tolls.
There we go.
They have to remember.
Yes.
I have to be wrong. Was it wrong? Not right.
So, if I was you, my community side. How you say cardboard box? Cardboard box and crew. Yeah, cardboard box, red cardboard box. What?
Easier, you know, walk to my school, find my Here's Columbia. No. That's the worst part when somebody gets moved from like out of the country. Oh, where'd you get that shirt? Oh, visiting Italy. Forget it. Forget it.
Day night, we make it one night. Next morning, wake up. Yeah. No, I can't do it. Boss, well, she had boss like make it fun. Then we see. Yeah, but sleep on it. Sleep on one trip. That's what. So no. Sure. Then we'll just check. I check the blood machine. See machine? You used to put your machine. You punch you out like that, we check it back out in the right like sure. So when it calm down, but then you got it to make sure you're alive. Because sometimes that we can also not go cut your pop. But just talk about yourself, I'm checking oil, blood, that's it. You got it. Don't worry. Girl. No, strong just no, no, yeah, professor, professor. Lecture lang sa pasa.
That's why you're not wearing the sleeve?
7, 8 minutes. 4 from my lab, chemistry lab. Then they pass with a C. And they have to go to college because they pass with a C in English with a C. And now they have to pay $2,800.
And what you mean about that whole
we take it and then we look zone, you see, and I have one that went to an English review. She got a 6 month because she got UVB. Now she has to go to Kaiser to the English to go to nursing program. It's a system. The 91, 92 English. It's a system. You got to get between 12 months and 8 months. You get 7 or 6. So the English day for 6 months. You need to get that's okay. Make sure you get paid and
that's why I was like the first thing was either
you want to get the GPA matters.
Like you went to Columbia to get a teacher, you get like, you go to Jamaica, actually Jamaica.
Those 2 classes.
Next thing you know, you're going to go to like,
just for that
Italy.
All right, guys, 1 minute till we start. So let's get ready for our quiz, please. Pencil, pen, eraser, calculator. No calculator, sorry. No calculator. Something simple for you all this morning.
Oh, I have a feeling what you're going to ask.
What you tell me? I have no idea.
Can I say it?
Sure.
You're going to ask about
Wait, do not say it, because what if it deters him from choosing that question?
the counting, the term, states specific numbers of items, like dozen, case, gross. Because that's the only thing with no calculator. I don't need a
There's
calculator.
another thing with no calculator.
All right, guys, let's get ready for a quiz, please.
Oh, you could ask them.
As always, you can seek the advice and help of a friend. However, you know, on an exam, you are on your own, right? So you may, just may, want to do it on your own. All right. I'm going to pop the quiz up here for you.
Ask the name of the dragon.
Here's your quiz.
Oh, you're right.
Balance that equation. 5 minutes. Balance the equation. 5 minutes. Oh, sorry, guys. Sorry. My mouse hit it. Sorry. About a minute left, guys.
I'm not there. I'm trying to figure out the U.S. side. I know how to do it. I thought this was on this side. This shit. It don't matter. Make it down. So this one, that's what confused me. Okay, so this is beautiful. This is new. Side beats. This side 6. Makes 6.
All right, there's your 5 minutes for that question. Not so bad, all right? And look at the question, please. What's your name on, by the way?
You can try. See what? Try.
That's what
You guys handing it in, or are you going to keep it? Last chance. Thank you.
Once your arms are cold,
All right, so moving right along. We have got a lot of ground covered, so let's start now. We left off talking about oxidation reduction, is that correct?
Yeah.
And we're going to start there. What is oxidation?
Oxidation is when they lose electrons because Leo says earth.
What's that?
That was it. Okay.
What's oxidation? Yell it out.
Oh, lose electrons.
Lose electrons. What else is oxidation?
Lose hydrogen.
All right. What is it?
And it has hydrogen.
Loss of hydrogen. Yeah.
Add oxygen.
What's the reduction then?
Yeah.
The opposite of all that stuff, right?
Yeah.
So an oxidation is first of all the gain of oxygen, yeah?
Yeah.
Or the loss of hydrogen. Or Leo the line says first. An oxidation is the loss of electrons. Fair enough, right? Let's talk about a quick, beautiful little reaction. Sodium plus chlorine. To give us good old-fashioned salt. Hey, look at that. Sodium and chlorine give you salt. Salt tastes good on everything. Now, let's take a close look at this reaction. Right now, there's sodium on the left-hand side. That's the element sodium. That's the atom sodium. So what is the important thing to remember about atoms? How many protons, first of all, does sodium have? $11. How many electrons does an atom of sodium have? 11. So it's negative 11. So an overall charge of sodium atom is 0, right? No charge. It's an atom, right? Atoms don't have any charges. Now people often say, well, how do I know that's the atom sodium? There's nothing written here. There's nothing written there, it's an atom. Now, every now and then, people will write this. They'll put a little 0 up there to hammer home the fact that leaving out the charge wasn't a mistake. We really do mean 0 charged atoms. Okay? Sometimes you'll see the 0 there, sometimes you won't. It just depends. Okay? So just know that if there's nothing written here, or if it's a 0, it's an atom. Same thing here, right? Nothing written here, yeah? So it's an atom. It's neutral. So, I know it's Cl2, I get that, but let's just work with one chlorine. It makes life easier. How many protons does one chlorine have? Positive 17. And if it's a neutral atom, how many electrons does it have? 17, right? With a charge of 0. So we're starting with two uncharged things on the left-hand side. Again, I know the chlorine is dimerized, 2 of them, but this worked with 1. This makes this kind of question a lot easier. Okay, now we look at this side of the formula, of the equation. Sodium chloride, that's no longer, well, the whole thing is neutral, right? But the sodium and the chloride certainly are not neutral, are they? What's the charge on sodium?
Plus 1.
Plus 1. What's the charge on chloride? Minus 1. Right? So we know that the sodium is always going to be positive when it adopts a charge. And chlorine is always going to be negative when it adopts a charge. You can get that from the periodic table if you forget. Now, that's cool. That's interesting. Because here the sodium was positive, neutral, and over here it's positive. Here the chlorine is neutral, over here the chloride is negative. So something's happening. Now, the easy way to do these questions, a really easy way, is to break it down by element. So look at the sodium and look at the chlorine independent of each other. Just do it. It's so much easier. Here's what I mean. Sodium on the left, 0, went to give me sodium plus on the right. That's what happened to sodium, right? That was the outcome for sodium. You guys understand what I'm saying? I ignored chlorine for now. For now, we're coming back to chlorine, but for now we're going to ignore it. Okay? Now, we already said that sodium has 11 protons and 11 electrons, right? The overall charge of nothing. Now we know, because we talked about this at length, that no matter what happens to an atom, unless it's a nuclear reaction, the protons stay the same, yes? It's the electrons that are going to change. So now, we have to have a plus charge, plus 1. So the electrons have to be what in order for this arithmetic to work? 10, right? Negative 10. In order for this arithmetic to work, there has to be negative 10 electrons here. Are you with me? That's just basic math, yeah? So we're going to go from left to right. Now we're only going to consider electrons. Let's imagine this is 11 tennis balls. And this is 10 tennis balls. They're not, they're electrons. So let's imagine they're tennis balls. As I go from left to right, am I gaining or losing a tennis ball? You're losing a tennis ball. I'm excited there. That's the first time it's written on that part. Oh, thanks. What if I dropped it? That would have been really embarrassing. No, thank you very much. We're going from left to right, you're losing a ball, right? Or you're losing an electron.
Yes.
And Leo, the line says Gur, right?
Yes.
Leo, lose electrons, oxidize. So going left to right, we've lost an electron. So this must have oxidized, according to the Leo rule. Is that okay? Does that kind of make sense? At least a little bit? Now, here's a cool little rule. You cannot have an oxidation without a reduction. They have to go together. They must. Because electrons are not allowed just to go off anywhere. They have to go somewhere. So from here, the sodium is losing an electron. Where do you think it's going? It's going to chlorine. Chlorine is taking it. Okay? Well, let's examine that. Let's make sure we're not saying, silly things. Now again, I know it's Cl2. You don't have to balance these types of questions. You just have to follow electrons. So just use, you ever see a dimer like Cl2, Br2, whatever, just treat it as 1. So this has got protons equal to 17, electrons equal to 17, an overall charge of 0. Over here again, the protons have to be 17 because the atoms never change protons. The electrons we have to figure out, but the charge has to be negative 1. So, this is true, this is true, this is true. So what must be true here? Negative 18. All right, again, consider electrons only. Going from left to right. Are we gaining or losing tennis balls? We have 17 balls here, 18 balls over here. Have we gained or lost? We gained 1 ball, right, or 1 electron. Good. Gain electrons, reduction. So we do this right, reduce or red or whatever you want to put here. This indicates reduction. So the sodium hands off the electron, that's an oxidation. The chlorine gained the electron, and that's called a reduction. Okay? I know it's weird. It's a reduction, is a gain, blah, blah, blah. It's weird. I get it. That's why we have Leo the line that says Gur minus. It's not so bad, right? This looks weird. It looks hard. It's not, though, is it? Not for you guys. We'll do another one then. One more. You guys will do one more. Me, I'm going to take a break. I've worked the whole 10 minutes. I'm going to go. All right, let's do another one. What if we had silver? Because you know I love silver. Sulfur. Give us silver sulfide. In this reaction, which reactant? Remember, reactants are things on the left, right? Which reactant is being oxidized? Which reactant is being reduced? Oh, you can't just look at the periodic table and figure out the charge of silver, can you? You gotta figure it out. See how all this stuff comes back into play? It's like we taught it to you for a reason. You can do it. It's a charge on sulfur. I'll help you out. Sulfur is -2, right? Sulfur is always -2 if it's an ion. So therefore, the charge on silver must be what? +2. Very good. All right, go from there. Starting to get worried that was me. No one ever calls me those bad names. Who's done? Wow, all right, not bad. Another minute, we'll go over together and we'll move on. All right, guys, how many protons does silver have? Whoa, 47. How many electrons does it have? Right. For overall charge of? 0. Oh, here we have silver plus 2, right? So the photons aren't going to change. Electrons, we have to do a little bit to figure that out. It has to be positive 2 at the end of it. So what negative number would that put there? Negative 45. So again, think of these as tennis balls. A lot of times we use the negative charges to teach people. So this thing was tennis balls. 47 tennis balls here, 5 tennis balls there. Have we gained or lost balls? We lost 2 of them, right? We lost a couple balls. So this is Leo. Leo, lose electrons oxidize. This is oxidation. Who got that right? Very good, outstanding. Outstanding. How many protons does sulfur have? 16. Must have 16 electrons then too, yeah? Overall charge of nothing. Protons equal positive 16. We know the negative charge has to be negative 2. It's sulfide, right? What does this negative number have to be? Negative 18. Right on. Very good. So here we have 16 tennis balls. We're going to get 18 tennis balls. If we have 16 balls, we know with 18 balls, have we gained balls? Yes. So we gained electrons. Gained electron reduction. Reduction. Whatever you want to say there. Okay? Who got that one right? Good. This will be on your next exam. Not this particular question, but it'll be on there, okay? Just a heads up. And when I say identify the reactant that's oxidized and the reactant that's reduced, for God's sake, don't circle the product. Okay? That's never going to be right, because it's the product. Reactants are always on the left, okay? You with me on that? All right. Did you guys all go home and read the chapter, or the part of the chapter I told you to on types of reactions? One person nods their head, the rest kind of laugh a little bit. All right. That'll be on your exam too.
What would be on the exam?
Types of reactions. Make sure you read it. It's not hard, just make sure you read it. Yeah, well, however you want to figure it out, just show me some kind of logical way you figured it out. Don't just guess. Yeah, if you went through this procedure, that would be fine. Yep. All right. Chemical quantities and reactions. I'll take a very simple reaction. Oh, and before I move on, I want to just say, a lot of students, they often start thinking stuff like, when am I ever going to use this crap? Right? To be honest, I know you're half of you are thinking it. You have this thing in your blood called hemoglobin, yeah? Right? And you all kind of love it, right? It keeps your body moving because it carries oxygen around your body. There's iron in hemoglobin, right? That iron will gain an oxygen. In other words, it oxidizes, right? Carries it around, offloads it into a cell, so the oxygen has to reduce at that point, right? Blood chemistry, a lot of it's oxidation reduction chemistry. I wouldn't lie to you about that, right? A lot of this stuff's important. You may not think it is right now, but it is. Okay! Here we have a very famous reaction. It's called the Haber process, H-A-B-E-R, German chemist in World War I, father of chemical warfare, was also the father of the Haber process. This may not seem like much to you guys, but he showed us how to take nitrogen from the atmosphere and convert it to ammonia, which maybe not to you seems like a very big deal. But before we had this reaction, there was no such thing as chemical fertilizer. No such thing. It's all biological fertilizer, cow manure, essentially. Now, because of the Haber process, we have a very quick way to make ammonia, which makes making chemical fertilizer easier and cheaper, and revolutionizing the agriculture industry just by doing that. Well, there's that too. Plus, you can ship this around the country, right? Anyway, very famous reaction. So let's balance it. You know, let's balance it. Go ahead.
Okay.
What do we do?
Count.
Just yell at me.
Okay, put 3 in front of the hydrogen.
Put a 3 in front of the hydrogen. Put a 2 in front of the nitrogen.
Yeah.
And that's it. That's the Haber process, balanced. Now, remember we talked about conservation of mass, we talked about how atoms on the left equal the atoms on the right, right? Y'all working on that? So does it make sense then that I can say this? 3 molecules of H2 plus 1 molecule of N2 will give me 2 molecules of NH3. Is that okay? It's true, isn't it? That's absolutely true. Now, I want you to think of this as a recipe. Like if you're going to bake cookies or something. A recipe, now, old school recipes, if you read them, like back in the day, they're written as ratios. You ever read those? You know, 2 parts flour, 1 part sugar, half part water, pinch of cinnamon. That's how they wrote them, right? Because the reason they did that was there was no such thing as a standard cup back in the day. You had what you had. Some people had measuring cups, most people just had cups, drinking cups, right? So you had to work in ratio. Okay? Same thing here. These are just ratios, right? I have 3 parts hydrogen, 1 part nitrogen. 3 parts hydrogen give me 2 parts ammonia, NH3. That's how this works. Are you with me? So I can have 3 molecules of this, I'm getting 1 molecule of that. That's my ratio. 3 to 1. Are you with me so far? Now, I could also say 3 dozen, right? Plus 1 dozen give me 2 dozen of these. There we go. I could say that too, couldn't I? That's no problem. This is just a word that needs a number, right? Right? So I just multiply by 12, right? So here I'd say 36, 12, 24. This is the word that needs a number. So I multiply this by that, and I get the number, right? So what's another word that needs a number that you guys know? Mole. Well, I can also write that, right? Write that too, couldn't I? Aren't all 3 of these essentially saying the same thing? It's just the numbers are getting a little bit different, right? Now, which one of these 3 do you think a chemist would most likely work with?
The last one?
The last one. Because there's that magic word, mole. We love that word. That takes into account a whole bunch of molecules. But it gives us really nice numbers to work with. Right? Are you guys with me on that? So I want you to look at this now. When you read this, I want you to say 3 moles hydrogen, even though the word's not written there. 1 mole nitrogen, even though the word's not written there. Gives me 2 moles of ammonia. That's how chemists, when we read these to ourselves, we read them like that. Remind ourselves these are 2 moles, 1 mole, 2 mole. And that's a ratio. Are you guys with me on that? Now, let's write the ratios down. Now, what I'm going to show you are the ratios for this recipe, for this equation. These ratios will only apply to this equation. They don't apply to any other equation. Just like if you're going to bake a cake, those ratios don't apply if you're going to make bread. Unless you like really sweet, floury bread. Which probably don't. Right? Good for you. I like my bread nice and firm. Bread that bites you back when you eat it. Alright, so I can say this, right? 3 mole of H2 equals 1 mole of N2. That's my ratio of hydrogen to nitrogen, right? That's how you write ratios, isn't it? I have 3 cups of this, I have equals 1 cup of that. That's a ratio. So that's an equality, yeah? And equalities easily become conversion factors. So this equality will give you 2 conversion factors that fit this recipe, but only this recipe. They won't fit any other recipe. So that becomes 3 mole H2 over 1 mole N2. Or, of course, 1 mole N2 divided by 3 mole H2. That's not something you haven't already seen before. We're just getting it from a different source. All right. if I have 1 mole, oh sorry, 3 moles, pardon me, 3 moles of hydrogen, how many moles of ammonia do I have? How many? Everybody. 2. 2 moles. You just get the numbers from here, right? It's the imaginary 1 there. That's where the numbers came from, right? So again, there's another equality. So again, we could write 3 moles hydrogen divided by 2 moles, right? 2 moles. And H3. Or, I think you're getting the picture. Hopefully. All right. What about if I had 1 mole of nitrogen? How many moles of ammonia can I have? 2 moles, right? And again, you could set the right conversion process over here. Okay? Now you're probably wondering why we're doing this. Why does this matter? Well, it'll do a big cake of E2. You got double the ratios, right? So we need 3 parts sugar, 2 parts water to make 1 cake. If you only have 5 parts water, how many cakes can you make? See? You have to figure that out, right? And it sounds like a daunting task. It's extremely simple. Honestly, it's extremely simple. As long as you have the recipe and your recipe's balanced, you can figure out anything from it. As long as you know 2 things, you can figure out the 3rd. It's very simple. Oh, sorry. Yeah, you 2 things. Okay? Let's see how. What if I told you that you are the manager of a chemical company that's making ammonia? And your people come and tell you that, hey, we only have 17 moles of hydrogen right now. How much nitrogen should we order? Common question. 17 moles of this. 17 moles of hydrogen gas on hand. Your people on your factory floor are going to place an order for some nitrogen. And they want you to figure out from them how many moles of hydrogen they should order. Because nitrogen, they don't want to have a stockpile, and that costs money. You want to buy just the right amount. So how are you going to do it? Well, you have to do a conversion, right? So we want to convert from this to this. We want to go from hydrogen to nitrogen. Are you with me? So that conversion factor, or that equality, will be 3 mole hydrogen equals 1 mole nitrogen. That's the conversion factor we're going to have to work with. Why? Because it involves the moles of what we have and the moles of what we want. All right, so here's how you set it up. This one looks very familiar. Mole of hydrogen multiplied by something will give me mole of nitrogen. Looks very familiar, don't it? Same thing we've been doing all year, for all semester. So what has to go down here? Moles of hydrogen. And what must go on top then? What is it? Moles of nitrogen. That's how it's set up, right? That's nothing new, is it? That's old hat now. At least I hope it's old hat. Now, 3 moles of hydrogen. So the number 3 must go there, correct? 1 mole nitrogen. So the number 1 must go up there. Everybody see that? 17 goes there. Divide 17 by 3. 5.6. Oh, round up.
6, 7. It's like the 6s that go on.
You need 5.7 moles of nitrogen. So that's how much you order. That's how much they deliver to you. And then you use it. And then you make ammonia, and then you sell it for profit. Okay? That's not an uncommon question. It's actually a very common question. Okay? All right, now, that's not much fun though. What's more fun is if I say, okay, we have 17 moles of hydrogen. How much money are we going to make? How many moles of this can we make? If I have 17 moles of this, how many moles of that can we produce? You guys try it. Similar procedure, be careful with your numbers. But the units tell you what to do. The units tell you what to do. They will never lead you wrong. Yeah, go ahead. I want you to tell me how many moles of this you can make from 17 moles of hydrogen. So basically the same question, but just go from here all the way to here, don't talk over this. Yeah? No. No, it's better than. Too soon to get bigger. Too soon. Roots. Yeah, what's the equality? Write the equality though, for what you're trying to do. 2 moles of what? 2 moles of NH3, right? Yeah, look, let's read the balanced equation. Oh, so that's where all the numbers are going to come from there. It's a little daunting when you first do them, but after you get used to them, they're actually very simple. All the way to the product. 9 moles of product. From 17 moles of H2. Who's done? Who's confident they're right and done? There you go. Good stuff. Another minute or so. All right, ladies and gentlemen, let me ask you a quick question. We want to know, we start with this many moles of that, right?
Yeah.
And we want to know how many moles of this we can make, yeah?
Yeah.
So what's our equality? 3 moles of H2, very good, yeah. And 2 moles of NH3, very good. So that's our ratio of hydrogen to NH3, 3 to 2. I don't know about you, but 3 to 2 ratio sounds intimidating. Can't just double it or triple it. strange number, right? So we're going to set it up the way we've always done it, right? Math's going to make our lives easy. Try to do it any other way. Fairly sure most of you will get confused. I know I will. And then they'll be like, well, they were just buying exchange tokens. There's our setup, yeah? What units go on the bottom? Very good. And on top? Very nice, very nice. There we go. Okay, what number goes on the denominator? 3. This comes from here, right? Number 2 on top, it comes from here.
Yes.
17 goes here. So you multiply 17 by 2 and then divide it by 3.
And you
You did? I don't know.
get 11.
11, really? Wow.
Oh, 11.3.
Oh, yeah, appreciate this. You get 11. Okay? Now, to me, that was a hard question. You can't just look at it and go 11. You have to actually do a little calculator. Okay? You done it right. Wow. All right. So you guys are awesome. Look at this. We can go faster. I'm just joking. Just joking. All right. Energy and chemical reaction. Yeah, I believe that's thermite. Yeah, it's thermite. There was a faculty member that used to do a thermite reaction on campus and then that fire started across the campus. So they asked me to do it. I said no. I'm good. I don't want to get in trouble. Because the reaction gets so hot, it will actually melt iron. So just imagine the heat. If you're evolving it, it's not worth it because someone can get really hurt. You know? If it goes wrong, it'll go wrong in a dramatic fashion. Anyway, energy and chemical reactions. So let's talk about energy. What kind of energy do we have? What are the two main types? Right. And what's the third one that we talked about? What's the T? That's the heat. Thermal energy, right? So, thermal energy is a type of, what kind of energy? Kinetic energy, right? So thermal energy translates into the movement of atoms or molecules, right? The faster atoms move, the higher kinetic energy they have, the more thermal energy they have, right? In other words, if you heat something up, the little molecules move faster, right? Cool something down, the little molecules move slower. That's energy. That's how chemistry, you should think about energy in terms of chemistry. Faster things move, higher their energy. Slower things move, lower their energy. That's how it works. Okay? Let's talk. Let's talk about chemical reaction. Oops, this slide's a little bit jacked up. Sorry. I'm going to fix it a little bit here. Sorry about that. I have no idea what happened there. Go away. There we go. It's somewhat okay. There we go. Something like that. All right. Sorry. There we go. Now, this is a chemical reaction. I'm going to just tell you how a chemical reaction works. You have to close your eyes and film with me somewhere else. It will mind you. Okay? Trust me, we're going to have a good time. Well, you guys are. Close your mind and let's get in our cars. Let's drive over to that awful, god-awful, horrible place in Coral Springs called that, what's it, Coral Square Mall? Now you go there now on a Friday morning, there's probably very few people there, right? Your odds of hitting someone or bumping into someone, or someone bump into you, is low, right? Your odds of collision, number one, are low. With me? The person has to have for a reaction to occur. Molecules must collide. They have to hit each other. Literally, they must collide. So if there's not many people in the mall, there's not many chances of collision. There's not many chances of reaction. Are you with me? But now let's go on a Saturday afternoon when it's raining. You can't even walk in the door. People are going to spend their money so fast. So what happens? You're going to hit people right away. Collisions are going to occur more frequently, right? So the chances of a reaction occurring go up dramatically just because people are there, or more molecules are there to collide with. Okay, with me? That's the first thing that has to happen is a collision. And I just proved to you that concentration matters. Concentration of people is low, collisions are random, or not very often. Concentration of people is high, collision happens all the time. And it's bad. Number 2, orientation. You have to hit people the right way to make them react. If I just bumped into you at the mall and said, excuse me, nothing's going to happen. We're going to go, oh yeah, no problem, have a good day. Usually, right? Usually what happens. But now if you hit someone the right way, if you come up behind them and shove them, that's going to cause problems, right? The energy's going to go up real quick, real fast, right? Same thing with molecules. If they hit in the right orientation, reactions will occur. But now, first of all, don't forget, they have to hit each other first. Now, they may hit each other 1,000 times before they do it the right way. Are you with me? And that's not enough. They also have to hit with this thing called the energy of activation. Now, what does that mean? It's a fancy way of saying they got to hit hard enough. Because really, let's imagine that you're in the mall and someone hits you in the back. Well, that might make you mad, but what if it's a little kid that just kind of shows you because we know children, that's what they do. Right? You're not going to react to that. It's not very hard hit. Why do you think of what I would do? Parents are really angry when you do that to their children. Understandably, I suppose. Now, what if a big burly dude like 400 pounds, like, whammo! That's hard hit. That's enough energy to cause a reaction. Right? It's going to be a fight. Probably. Okay? You all with me on that? So, the chemical reaction, you have to hit in the right orientation, and you have to hit with enough energy or speed to cause a reaction to occur. In other words, have you ever wondered why you put your food in the fridge? Ever wondered that? Like, why do we throw food in the fridge? To slow down the process of boiling, right? Well, boiling is a chemical reaction, a natural chemical process, right? Because, you know, when things die, they decay naturally, right? Something's already dead, like a meat, you throw it in the fridge. You slow down the natural decay process. What are you doing? You're slowing it down so the little molecules that are going to decay your food cannot reach this. They cannot hit hard enough. You ever cut an apple in half? Watch it turn kind of a golden brown color? That's oxygen reacting with the fruit of the apple. Reacting with the sugar, actually. Okay? Now take that same apple, cut it in half, take one side of the apple, wrap it in plastic wrap. Tight. Nice and tight in plastic wrap. Put both parts in the fridge. The one that's not wrapped will still react, but slower. Right? The one that's not wrapped will react, but slower. The one that is wrapped will still react eventually, but a lot slower. Are you with me? Why is that? The one that's wrapped can't get too close. Are you with me? When it can't collide, it certainly can't collide the right way. So that's what you wrap your food too. You're trying to prevent more collision with literally trying to prevent oxygen collision. Does that make sense? Isn't that neat?
Yeah.
Yes, Dr. Pence. We're so happy that you're passionate about this science. Your whole life's work is a sham. Write that down. Exothermic. Correct. Exothermic. An exothermic reaction is a reaction in which heat is released from the reaction. In other words, energy is released from the reaction. Now, the word exo, or the prefix exo, means to exit, right? Have you read the signs that exit? Exo is the prefix, right? It means to exit or leave. Thermic is the word for heat, right? But exothermic, leaving heat. The heat is exiting the system or leaving the system. What does that mean? Well, that means that as far as you're concerned, the observer, me and you, the surroundings are getting hot. Let's talk about that for a second. Let's imagine that you all are a reaction. You guys are all colliding, you're all reacting with each other, and you're giving off energy. You're giving off heat. So from your point of view, you're giving your heat away. So you're cooling down, right? Imagine a frying pan on your counter that was red hot. Now it's cooling down. The frying pan itself is getting colder, right? But the surroundings are getting hotter, right? You put your hand by that frying pan, you can feel the air is hot, right? Put your hand on the countertop, you're going to feel that countertop hot too. So everything around the thing that's giving off heat is getting hotter. The thing that's giving the heat away is getting cooler. Are you with me? Exothermic. We, the observer, find the heat. That's where the reaction of chemicals are giving the energy away. Does that make sense? Okay? That's pretty easy, right? Yeah, we're giving our energy away constantly. We're exothermic. The reactions in our body are exothermic.
That's why our bodies are much older.
Yeah. Oh, well, when we die, we get cold. When we're alive, we get hot. Sure, I can try to answer it. All right, that's exothermic. All right, now what I want to point out to you here on this little graph, this is the energy at which the reactants are starting out. So this is just some molecules at a certain energy. The energy number doesn't matter; they're at a certain energy. And when they collide, when they actually hit each other, their energy actually goes up. Okay. Now, what I want you to understand, the top of this energy pump, top of this graph, this little crescendo here, that is the energy of activation. That's how much energy you have to hit with in order to have a reaction occur. If you can't get your energy to here, a reaction will never occur. It has to get to here. So this is how hard they have to hit. The speed they have to hit with. And once they do that, they'll come down the other side of this graph, and here, the energy was high, they're going to a low energy, they're releasing energy. Okay? The energy of activation is how much heat you have to have in your system before anything will happen. Okay? So if it's too cold, nothing's going to happen. It's just going to be warm. Okay? You with me on that? A little bit? Okay. Endothermic, write that down. Endothermic reaction is opposite of exothermic. The word enter starts with en, right? Prefix en means to enter or come in. So endothermic reactions, heat is entering the reaction. Heat is going into the molecule. The molecules are absorbing it. You with me? So now, here's the fun part. You guys are in the reactor, and you're trying to react. But to do so, you must absorb heat. You must draw heat into yourself. In other words, you must get hotter. Yeah. Why? Because you got to move fast. Okay? Where are you going to get the heat from? You're going to get it from everywhere else, from your surroundings. Me, for example. So let's imagine this is where the glassware stops. You guys are inside the glassware. And the environment's out here, the air. You guys are demanding energy. You're actually, seriously, you're sucking it in from the environment. You guys are getting hotter, but the environment is getting colder. Right? So cold, it could cause frostbite in some reactions. It's so cold, the strands will get so cold. That's called an ice bath, right? People, the little packs, they break it, they shake the hell out of it, and they slap it on your ankle. That's an endothermic reaction. It's so cold, it pulls the ankle down. Right? They have to break the pouches, right? And then shake. The two reactions are separated by pouches. You break them, you shake them. You mix them, then they go. They suck all the energy from, well, not all of it. They bring in energy from the environment to cool you down. Neat, huh? I think that's pretty cool. Punishment. You wait to do that for 2 years. Thank you. All right. Here's an excellent endothermic reaction. Again, the top of the peak, the top of the hump, that's the energy of activation. You've got to get to there before the reaction will occur. You've got to get there. So this reaction is going to draw in a whole bunch of heat to get there. It's going to make the surroundings feel ice cold. Very, very, very cold. And that's it for this chapter. No, sorry. One more thing. Oh, that was it for this chapter. Reaction rate. Now, reaction rate is a very simple concept. Folks try to make it complicated, I think. Reaction rate. How fast are you going? Are you making 1 molecule an hour, or are you making 10 molecules a second? Your speed of the reaction. Now, what do you want to keep in mind? When the temperature of a reaction rises, the molecules move faster. So the reaction rate can go up. Just imagine now, if you're at the mall, and instead of everyone strolling, they're running. And if everyone's running full speed, whenever you hit, you're going to react. Everyone's moving so fast. Okay? But now let's imagine you take that same people in the same mall, and instead of running, they're walking with little baby steps. Even if you bump into each other, it's going to be kind of funny because everyone's walking with baby steps, right? So no one's going to react. It's going too slow. So that's again why we throw the things in the refrigerator. We slow the molecules down so they can't react. Drop the energy, so the energy activation can't be achieved. Same reason why you freeze things. If you freeze things, the molecules almost completely stop moving.
So, if you slow down, so if I get like cold from you, is it already cold?
Yeah, pretty. We have a cooler that's
You mean
moving
like
down.
before the ice?
Yeah.
Something has to slow it down.
They usually cool it. Well, it won't spoil, no. If there's preservatives in it, it won't spoil. But if it didn't have preservatives in it, it probably would spoil it. But also, with when you use the canisters, those canisters you see up in the air, so it probably will last a pretty long time. But if you just have like Coca-Cola without any preservatives in it on your counter at home, it will grow mold probably overnight. Because there's mold in the air, and there's sugar in the Coke, and there's water in the Coke. But there's also acid, so that might help a little. I don't really know if it'll grow mold or not, but it's the acid. Sugar in the water definitely will grow mold. So the acid might prevent that from happening. And then they throw in a preservative called sodium benzoate. Sodium benzoate is there so that you don't get mold. It's an antifungal. So believe it or not, most of our foods eventually will grow mold. But if you make bread at home, if you just made a little bread that's homemade, if you leave it out, it'll go bad in a couple of days. It'll grow mold in maybe 5 days. But roasted bread in the store that's been preserved will grow mold probably for 2 to 3 weeks. Because the chemical preservatives in there. And some people say it tastes bitter. I don't personally think so. And if you keep it in, again, if you keep the reactions go fast. Right? Of course, it's going to be boiled. Okay, so that's reaction rate. Catalyst. You've all heard the word catalyst before, right? Catalyst is something that's in a reaction that helps it go fast. It will speed up the reaction rate. And how does it do that? It's very simple. Take a look at this green line right here. This green line is the reaction without a catalyst. So there is no catalyst in this reaction. Look at the peak, the energy hump. It's way up here. So it's going to take all this energy to make the reaction go. If you throw in a catalyst, the heat required goes down dramatically. Like, I mean, seriously drops. So the reaction will go faster. Now, in your body, same thing, and we're going to go to chapter 16, your body has catalysts called enzymes. And enzymes actually catalyze almost every reaction in your body. But believe it or not, most of the reactions that we have in our body wouldn't work fast enough if we didn't have enzymes. Enzymes make them happen fast so that we can get things that we need. Okay? So catalysts is a big deal. We'll come back again in chapter 16. But just for now, know what it is and know how it works. It lowers the activation energy. Making the reaction go faster with less heat. Okay.
If someone, like, let's say, like a regular person had all their catalysts removed for like a day, how long would they survive?
I don't know, not very long. You know these things to break down food stuff. To break down cells, so I don't think you live very long. Plus, if you lost your hemoglobin, you're kind of screwed. All right. Yeah, we did that already. Good. All right. On to the next one. Now, chapter 8. I'm moving it to the end of the class. Okay? So in the syllabus it says chapter 8 is right now. I'm moving chapter 8 past chapter 16. Okay? Chapter 8 we can go over in 20 minutes, so I can make it a reading assignment if I absolutely have to. It's not hard. Chapter 9, however, is somewhat involved. So we're going to skip 8, put 8 at the end of the course, and move on to 9. Solutions. Write that down, please. Solutions. Solutions. This is the title, chapter 9, solutions. Solutions are homogeneous mixtures of two or more substances. What's homogeneous mean? Same? Uniform? Uniform throughout. Very good. Now, there's two components in the solution. One is called the solvent, one is called the solute. You can have more than one solute. You can't have more than one solvent. Okay? Two components, solvent and solute. Solvent is present in the solution in the largest amount. That's how you know it's a solvent. Solutes are present in lower amounts. That's how you know they're a solute. Okay? So if you're not a solvent, you must be a solute. Is that okay? This is the opposite. And the book in the slide is showing you a photograph of salt going into the water. In this case, the water will be the solvent, and the salt will be the solute. It's being dissolved by the solvent. It's being dissolved by the water. And water is one of the more common solvents in the world. Yeah, you keep it solid, like without water. I don't think salt will do that. Salt will eventually just settle to the bottom, but there are some things that will do that, like alcohol, for example. You can have a 49% solution of alcohol, where it's, say, 49% alcohol, 51% water, and water is your solvent. You can also have a solution of 49% water, 51% alcohol. You can do that. It's very easy to do. In that case, the solvent flips to ethanol. So it's alcohol. Because the reason that works is both things, both water and ethanol, are infinitely soluble in each other. So that's it's a rare case. It doesn't happen very often. But yeah, it could happen. All right, solutions. There you go, huh? Solutes can be liquids, gases, or solids. They spread evenly throughout. In other words, they're homogeneous. They mix with solvents, so the solute and the solvent have the same physical state. In other words, you dissolve salt and water, both the salt and the water are liquids. Okay? They cannot be filtered. But they can be separated by evaporation. You guys know that, right? You take some salt water, run it through a filter, the salt runs right through the filter. Doesn't care. Doesn't care at all. But if you boil the water off, the salt at the bottom, right? That's true, isn't it? Okay. And solute, this is a key point, solute is never visible, but it may give the solution some kind of color. Now, while you're writing that down, I want you to think about the best solution, pardon me. Huh? I can't hear you. Oh, okay. The best solution ever is, anyone know? Kool-Aid, yeah. You've heard the story before, I guess. Kool-Aid. Why is Kool-Aid so darn good? No one knows. It's a mystery. But how do you make Kool-Aid, right? Water, sugar, and the Kool-Aid package, right? That's how you make Kool-Aid. Yeah? Nice, beautiful, simple. So now, in that solution of water, Kool-Aid, sugar, what's the solvent? The water, right? The water's the solvent. There's a half gallon of water in there, right? I haven't made Kool-Aid until I was 12, and I know the recipe. Half a gallon of water, cup of sugar, and the Kool-Aid pack. That's another. That's awesome. Now, what are the solutes? There's two of them. The sugar and the Kool-Aid. Those are your solutes. Now, I think everyone will agree that's a clear solution. You can see through it, right? But it certainly gave the solution some kind of color, yeah? And what's your favorite flavor of Kool-Aid? Children will always say color. Red. Red is my favorite flavor. No? Then it gets confusing for children, right? Because you say, oh, no, colors aren't flavors. And then some kid who's really smart goes, what about orange? you got me. That's a great comment. I'm sorry, I can't answer your question. Right? My favorite was, I like purple. That was a fun time of life. All right. Water is a solvent. Water is one of the most common solvents in the world. Now, don't get led down this idea that water is the only solvent. It's not. But it's a very common solvent. Very common solvent. Sometimes it's referred to as a universal solvent because it dissolves darn near anything, but not everything. Okay? Now, remember we talked about water? We talked about bond polarity and all that? We talked about hydrogen bonding? Delta positive hydrogen, delta negative oxygen. And that was pretty special. Kind of made water a unique thing. That really is unique. There's other things that do it, but water does it really well. That's what gives water the ability to dissolve a lot of things, right? because it just has that unique structure, unique properties that let it do that. That's why it's so important for biological systems. Now, when water dissolves something like, say, sodium chloride, what it's going to do is it's going to take the sodium, which is positive, right? And this is a delta negative right here, right? So that delta negative is attracted to that positive charge. Does that make sense? What the water will do is it will surround it. Many, many water molecules will surround that salt, that sodium. I'm not sure how many, around 7 or 8 that will go around it. Now I'm drawing it on a flat surface, but you have to imagine in your mind that these waters are going to form a sphere, a big old sphere around that sodium, right? But they're going to do the same thing to chloride too, only it's going to be the other way. Instead of the oxygen spacing it, it's going to be the hydrogen spacing it. The hydrogens are delta positive, chlorine is negative. Okay? Now that allows the sodium chloride to actually separate while it's in water. Okay? For those of you who've taken lab, that's called an electrolyte, right? Separates the charged particles in water. That's actually amazing, right? Now imagine that you're a prehistoric human, right? And you find a rock, and sodium chloride crystals look really pretty. You know, they're kind of whitish, translucent a little bit. And imagine you're a prehistoric man. What are you going to do? You're going to lick it, right? It tastes good. You lick it, it tastes good. So then, because you're a prehistoric man, you probably throw it to a mud puddle or something, and it freaking disappears. Imagine that you're a prehistoric man. You've never seen that before, right? How fascinating is that? Throw a rock into water and disappear. That's how fascinating prehistoric humans must have been by that. And then they come and drank the water. Right? It's salty, right? You have to admit it to yourself. Salty food tastes good.
Right.
I didn't say it was good for you. It just tastes good. No, not salt water. Not salt. Not salt. But I will say this: if you go to the beach, go for a swim, get a little salt water in your mouth, bite into an apple. The apple never tastes better. Seriously, try it. Go to the beach, go for a swim, you get water in your mouth, salt water, right? Then eat fruit, bananas, oranges, mango, any fruit. It'll taste immediately, like a million times better than you ever think it could.
The contrast of like the salt and then it tastes weird.
Doesn't taste weird, it's better.
I said weird.
Better.
Like, because I know.
Better.
We do a lot of
Better is
restaurants-
not weird. Better is better.
Because a lot of restaurants will put like salt on top of the ice cream so
Yep.
that when you buy the ice cream, it tastes even better.
Exactly. Don't ever do this because it's really bad. If you bite into an apple, put a little salt, bite into it again. Woo. Never eat apple, more salt again. And then you get high blood pressure and die. You know, whatever. It's worth it, right? No, I'm serious. Try it once. Just try it once. It actually does make the apple taste a lot better.
Put salt on
You can. Well, that's what you hear bakes, right? You know bake?
Yeah.
Isn't salt an ingredient in all baked goods?
Yeah.
Right? Why do you put it in there?
Makes it
Makes it sweeter. Makes it taste better. Right?
sweeter.
Well, you add salt. If you add salt, it comes out bland. Everyone thinks you can't do it.
Yeah.
You ever have a dinner party and things go terribly wrong with the food? That's how you fix it. Butter, salt, garlic. Everything's better. Oh, that's how you fix it. Everyone's like, how did this taste so good? Oh, I don't know. Butter, salt, garlic. That's how you do it. All right, write this down. Like dissolves like. Very important thing. You're going to hear me say it 2 times. So we're going to put it right now. Like dissolves like. Now, what does that mean? Very simple. That means polar molecules will dissolve polar things. Polar molecules dissolve polar things. That's right. Contrast to that, non-polar things will dissolve non-polar things. That's kind of how it works. So water is polar. Water will dissolve anything that's polar, for the most part. Okay? Salt, for example. Water can dissolve most of them, not all of them. Okay? Now, non-polar, let's think of a non-polar thing. Probably the most common non-polar thing that you guys have experienced with is gasoline. Gasoline comes from oil, and oil is non-polar. Vegetable oil is also something you guys are probably familiar with, right? Now, you ever go to the store, go to the salad dressing aisle, this is where you'll see it. The salad dressing has olive oil in it, right? Go buy it. Now, I'm not marketing a brand here. This is a brand that I know demonstrates it. We're from Italian. Which from? they have that little layer, right? There's the olive oil on top and the water on the bottom. So that is showing you that life is all life. The Italian salad dressing, the olive oil is non-polar. Oils are non-polar. Water is exceptionally polar, right? Water from the bottom. They won't mix. They'll never mix. You might say, well, when you shake it, they mix. Well, they don't actually mix. They do what's called emulsifying. Right? A little oil will kind of suspend itself in the water for a little bit. And then you pour it on the salad and it tastes really good, right? That's life dissolved life. So if you ever pick up a wistful Italian salad, if you ever pick up a salad dressing in the Italian style and it's not layered, they've added something to it to keep it from separating. That or they never added any oil to begin with. So buy the good stuff. Or better yet, make your own at home. Tastes better to make your own. Okay, moving on. Electrolytes and non-electrolytes. Electrolytes and non-electrolytes. Now this is something that you probably all heard of. Most of you take lab, by the way, right? Electrolytes and non-electrolytes. And our country is really good, or the companies that are in this country are really good at marketing, right? So you've all heard of electrolytes. You all have to replace them.
Oh,
right?
Gatorade.
Yeah, Gatorade. You have to replace electrolytes. Has all the electrolytes your body needs. You know, also a lot of sugar. So now, what's an electrolyte? First things first. Electrolyte is charged ion in the water. Saying charged ion is kind of redundant, but you get the idea. It's a charged particle or an ion in water. Okay? That's what an electrolyte is. Electrolytes come in two varieties, strong and weak. Okay? Strong and weak. Now, strong doesn't mean it will hurt you. Weak doesn't mean it's benign. In fact, the most dangerous electrolyte I know is a weak electrolyte. Okay? We'll get to that. Now, the most common one I know is a strong electrolyte, sodium chloride. Strong electrolyte. What does the word strong electrolyte mean? Very simple. It associates 100% in water. Well, what does that mean? It means it completely separates in water. So let's imagine we had ourselves some sodium chloride in a box, which is solid, right? We're going to add some good old-fashioned water to that, and we're going to get sodium plus Cl minus. Aqueous. What's aqueous mean? Very good. Dissolved in water. So now, take a look at this. Let's read this equation together. Sodium chloride, solid. So it's from a box. We add some water, and we get sodium positive dissolved in water, right? Chloride dissolved in water. We don't have an aqueous by this, do we? This says X, right? So this sodium chloride is not dissolved in water. Are you with me? It can't be, it's a solid, right? If it was dissolved in water, I could put an AQ right here, couldn't I? Well, this is telling me that in the beaker, I take my sodium chloride, so I'll just take a spoonful or whatever of the solid, and I'm going to get Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. But nowhere in this container do I have this. Not there. But there is a whole bunch of sodium ions and a whole bunch of chloride ions. Completely dissociated. Dissociated means these ions separated into their constituents. That's what dissociation means. 100% dissociation means it goes all the way from here, 100% to these things. That's what 100% dissociation means. Now here's a fun fact. If you pass electricity through this, it will conduct it very well. These electrolytes can carry the charge. Okay? And we did this in 1032 lab, for those of you who took it. We had a little, we had this demonstration right here, essentially. We had a light bulb that was plugged into the wall, and we had this broken circuit right down here. These wires are not connected. We dipped these wires into a strong electrolyte solution, and that light got really bright really fast. Right? Remember that?
Yes.
Strong electrolytes can do that. Strong electrolytes make that light really bright. Weak electrolytes, on the other hand, don't make that light very bright, they make it very dim. We'll talk about those in a second. Okay? Strong electrolytes, 100% dissociation in water to give you the ions. Strong electrolytes, strong electrolytic solutions can conduct electricity. Now, be careful. Sodium chloride is a solid, granular sodium chloride that you buy from Publix in the solid form does not conduct electricity very well. Okay? You have to dissolve it first. Once you dissolve it, then it can conduct electricity. Okay? This is also why you don't take a shower or, well, a bath especially, with any kind of radio or electronic device that can fall in with you, right? Because if you have bath salt, it can conduct electricity and kill you, right? Right? Yes. But none of you even know what a radio is, do you? You all have iPhones, Androids, iHeartRadio. It's a strange world we live in. Weak electrolytes. Now, weak electrolytes will dissociate in water. They have to dissociate in water. Just about 100%. But, in fact, they dissociate very, very, very minimally. They don't do very much. Let's take a look at that. How we would write that. A weak electrolyte. Now, every book in the world uses this example, so I'm going to use it too. Hydrogen fluoride. HF. Arrow to the left, arrow to the right, water up here. H plus, F minus. Now watch what I'm going to do here. Everybody's aqueous. Everybody's aqueous. Oh, that must mean the parent molecule that we start with, hydrogen fluoride, dissolves in water but doesn't dissociate. Yeah? And maybe one or two molecules do, we get some of this H plus, this F minus. So everybody, all three components, the parent molecule and the daughter ions, are dissolving in water. Are you with me? So if you add a bunch of HF, I believe it's a gas, you will get a whole bunch of HF molecules floating around in there. Well, not floating around, dissolving. But and a few ions. Notice I only do 2 ions, the rest of the parent molecule. That's generally what you see in a weak electrolyte. You see a lot of the parent molecule, but not a lot of the ion. This is how they work. Okay? Now, if you were to stick electrodes down in there or pass electricity through it, this solution would definitely light the lamp, but it would essentially make the filament glow. Essentially what it's going to do. Okay? In lab, for those of you who took lab here on North Campus, you would have seen that. The weak electrolyte solution with vinegar, and that light, the filament barely glowed, right? You barely get it to glow. And you had to work at it to make it glow, right? They don't conduct electricity very well because you don't pull out ions. Okay? Now here, dangerous electrolyte. It's extremely dangerous. Hydrogen fluoride. This is a real quick story, then we're going to take a break. Hydrogen fluoride. It's industrial use. You're never going to believe this. It's kind of cool. It's industrial use is to etch glass. So you draw a little design, you can pour some of this acid over the design on a piece of glassware. It will dissolve the glass and put the design in the glassware. Okay? It's used for etching. Okay? So imagine this for a second. That'll dissolve glass. Not many things dissolve glass, but this will. And that's pretty cool by itself. Also, most things that have fluorine attached to them have an easy time going through your skin. Called being transdermal delivery, right? So that's okay, fine. It'll go through my skin, right? Well, you say that now. If it goes into your skin, you're going to get it goes through your skin into your blood. Your blood's made mostly of water, right? You're going to get a bunch of these ions in your blood. Now you're going to say, well, wait a minute, Dr. West, you drink fluoride. Well, drinking fluoride and getting fluoride directly in your bloodstream are 2 different things. You can drink fluoride ions. That won't hurt you. If you inject fluoride ions into your blood, that will kill you. Okay? A whole different ballgame there, right? The F minus loves calcium. It loves calcium. Like, it will react with calcium over anything, or preferentially over most things. So when that happens, it'll form CaF2. And you're like, okay, what's the big deal? Solve it. Get the big deal now? Form solids in your bloodstream. That's not good. These solids tend to accumulate in your joints. And you get severe arthritis, I've been told. And it also can kill you, right? Because it will also weaken your bones. How does it do that? Well, if your calcium level in your blood drops below a certain level, your body will do what? It'll make it up. From where? Where's the biggest calcium source in your body? Your bones. It'll weaken your skeleton. If you get enough of it. Now, if you get a little drop in your hand, I don't think anything's going to happen to you really bad. If you get a big spill of that on your skin, it'll hurt you. And it'll be a life-changing event, for sure. Right? Pretty cool, huh? That one. Yeah. Sort of fun. Whoa! So, I don't work with it. One of the few chemicals in the world I actually refuse to work with. If I'm not careful. I mean, I'm careful, but that is a whole other level of carefulness. Cool, huh? Everyone loves hearing stories about death and pain. I don't know what it is about humans, we all love it. All right, back in 10 minutes, please.
You on campus Monday or no?
Oh, I have class all day though.
Oh, I can't even catch you early in the morning. You know, come to your class and just pick up the paper or no?
Oh yeah, sure. Yeah. Like early morning Friday, or maybe 9 o'clock.
Are you in the same room, huh?
No, I'll be in another room. I'll be in my office.
Oh, okay.
Yeah. You have 45 balls here, right? Sorry, you have 47. You have 45 balls, right? So going from left to right, you've lost 2 balls. Let's feel the lines of curve, lose electrons oxidized. We're going from here to here, you've lost electrons. Think of them as chemical oxidation. This one here. Yep. This actually lost. It's not a reduction, it's an oxidation. Very quickly, diving on this one. My boss. What did I do?
Not you. It's our last meeting.
What did I do? I'll be fine. Getting warm again outside. Winter's over. It's funny, the temperature goes below 70, everyone starts putting jackets on.
I mean, yesterday morning, I wake up around 3 every morning. So yesterday morning it was hot. It was not yesterday.
It was weird, because you walk out of your house, you figure it's going to be hot, and it's like, whoa, you bet you a sweater. Then I wear a sweater, everyone's like, you're a Canadian, you're supposed to like it cold. I'm like, said that. So that's why they're all down here in the winter time.
Yeah, I think.
I do like the cold weather, that's why I go up there every year, but I don't want it all the time.
You're supposed to get a warm weather back and rain, it's supposed to be raining.
Typical Florida weather. But then again, you commit. In December or January, into February, this is the place to be.
Yeah, it's not.
I like it. It gets hot during the day, and then you go back down at night. I mean, it's like 80 to 75, but still, for us, that's cold, right? You go, woo, it's cold. All right, guys, that's our 10-minute warning. Welcome back. For those of you who are back. All right, so I wanted to remind you, because I was reminded this morning, that we actually don't have any class on Veterans Day. That is a holiday. So I will not be here on Veterans Day, and I guess that's a Friday, right?
Yes.
No, Veterans Day. Is that next week? I don't know.
It's a Friday.
2 Fridays from now?
Yeah.
So it's definitely a Friday? All right, so there will be no class on Veterans Day, which is 2 Fridays from now. So don't come to class, okay? According to this, the school offices will be open. If you have any business with the school, it might be good to take care of it, okay? Because it's probably bring in people. But if you have business with the school. So please, tell your friends, tell your neighbors, tell everyone you can think of that we don't have class on Friday on Veterans Day.
Dr. Les, so your exam is on November 17th, the Friday after?
Don't know. I believe so. Is that what it says?
I think it's yeah. I think it's November 17th.
I believe. I do it myself. I don't know. All right, moving on. Non-electrolytes. Now, I don't want you guys to think that everything has to be either an electrolyte or a strong electrolyte or a weak electrolyte. There are a lot of molecules out there that will dissolve in water but will not conduct electricity. They're non-electrolytes. So non-electrolytes will certainly dissolve in water and will not produce ions. And the greatest example of that is old-fashioned table sugar. If you dissolve table sugar in water, that solution that you make is not going to conduct electricity at all. Okay? But it will taste good. I'll stop trying to talk about this kind of fall back on chemistry. This is why I never became a comedian. All right, so we have weak electrolytes, strong electrolytes, and non-electrolytes. Okay? So don't fall into the trap of thinking everything has to be an electrolyte. A lot of things indeed are not. Okay. Wait for what? Non-electrolyte. Don't worry about equivalence. Solubility. Solubility. Put the title down. What are we using here? Solubility. Title. Solubility. 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 The title is all you need. Solubility. All right, solubility. It's a very simple concept. It's a very simple concept. It's the maximum amount of solute that dissolves in a certain amount of water. How much can you dissolve in a certain amount of water? It's easy, right? What? Yeah. Breathing in there. Florida. Florida in the wintertime. It's cold. Okay? Solubility. Now, I want you to understand something really quick. Temperature sensitive. Wait, what? Yeah. Let's think about something real quick. It's Friday. Most of us are probably going to go out and have a good time tonight. I will be home grading papers. You're laughing, but it's true. My life is boring, and I kind of like it that way. You know, I have a comfortable couch and a big TV and a nice stereo. I'm good. Now, if you wanted to make something, say, adult on Friday night, you might go to our old friend, mojito. Everyone likes to do mojito, right? What's a mojito made of? Sugar, mint, limes. Missing the key ingredient. Alcohol, some kind of rum, tequila, vodka. Probably tequila because it's a Spanish drink. Mojito. It's rum? Ah, well there we go. It's rum. There you go. Now, you could be fancy. You're too young. You shouldn't listen to this. I'm not talking about the internet. I'm not talking about alcohol. Now, how do you make a mojito? Well, the first ingredient in mojito is really, they call it simple syrup, right? Simple syrup. And you can buy simple syrup from the store. It's expensive. For what it is, it's very expensive. Well, you can make your own. Simple syrup is essentially water dissolving sugar. But to make simple sugar, you have to heat up the water. Why? Because it increases the solubility of the sugar. Okay? You're actually taking sugar past the solubility point by heating it. And then when you cool it back down, the sugar takes a long time to come back out of that solution. So it makes the syrup. The water that you're dissolving it in gets very thick. Okay? And then you grab some fresh mint, bottle it up, pour in the rum, swirl the rest of the nice mint flavor into the rum. The alcohol dissolves mint flavor, right? Pour some ice, pour some syrup. Done. Drink it. I didn't give you the whole recipe. That way, you can't say that I encourage you to drink. In fact, I did not. Unsaturated solutions. Write that down. Unsaturated solutions contain less than the maximum amount of solute. That means you can add more solute. Let's go back to Kool-Aid. Because Kool-Aid is one of the best solutions out there. How do you make Kool-Aid? We already talked about this. Cup of sugar. 2.5 gallons of water, Kool-Aid package, right? That's what your mom is looking, right? So every kid in America has done this. How do you make Kool-Aid taste even better? You add another cup of sugar, right? That's how you make it taste better. And that cup of sugar dissolves, doesn't it? Everyone's done it, it dissolves, right? Because the original Kool-Aid solution, the way you're supposed to make it, is an unsaturated solution. You could, and we proved it as children, add more solute. Stir, and it dissolves, right? And it tastes a lot better. It's going to rot your teeth, but it tastes a lot better. Right? It's really catchy. Don't do it. Don't even, if you're an adult like me, like over 40, don't even try it. Very other thing, like water. Now, that's cool. How do you remember this? It's very simple. If you have a big shower, right, or you go to the beach, you have the water, you dry with a towel, right? Is that towel completely soaked with water? Are you sure? You just dry your hair, the towel is soaked with water? No, you just kind of dry yourself off. The towel is still usable, right? You can still dry yourself off 2 or 3 more times with that same towel, right? Because that towel is unsaturated. Now let's imagine you go to the beach with your friend, and when your friend grabs your towel and runs to the ocean with it, and runs back out. Could you use that towel to dry yourself with? No, why? It's saturated, right? The water has a saturated towel. So a saturated towel can't hold any more water. A saturated solution can't hold any more solute. Okay? Unsaturated can hold more. Unsaturated can't hold any more. Here's saturated solution. Saturated solution has hit its solubility point. You cannot add any more solute to it. It will not dissolve. It will not dissolve. Okay? And you know you hit the saturation point when you add more solute, such like salt or sugar, and it just settles at the bottom of the flask. If you all done that experiment as well too as children, right? If the 2 cups of sugar are good Kool-Aid, 3 must be better, right? Put the 3rd cup in, what happens? Goes to the bottom. Christina, you've done this. Good job, Christina. Exactly, right? When you add that 3rd cup, the sugar goes to the bottom, and then what? Your mom is going to catch you. You are busted now, right? You're done. Mom is going to know you sweeten the Kool-Aid. How do you fix it? You can add more water, or you can heat it up. You can warm it, right? You can heat your Kool-Aid up. Because remember, solubility is temperature sensitive, right? You heat up the Kool-Aid, the sugar should dissolve into it, you make like a Kool-Aid syrup, right? And what's that called? When you take a solution and heat it up past the solubility point. That's called supersaturated. S-U-P-E-R, supersaturated. When you go beyond the solubility point by heating.
You don't do that in the lab?
No, that's too messy. I'd like to, but it's really messy. Plus, it attracts ants. It's Florida, right? Ants are everywhere. Now, you've all experienced supersaturated solutions and just didn't know it. You've all eaten honey before, right?
Yeah.
Honey is a supersaturated solution of sugar and other things in water. And how do we know it's supersaturated? Well, have you ever had your honey sit on the shelf for a couple months and then it turns into a solid? Yeah. That's solid sugar, right? That's the sugar. How do you fix it? Warm it back up, right? So aren't you making a supersaturated solution? Right? You've gone past the solubility point, it's solidified again, you run under hot water for a few minutes, it goes back into solution. Right? Supersaturated. Isn't that cool? You don't like honey either? Thank you. At least one person likes it. Thank you. One person. Alright. Don't worry about any of this stuff. Don't worry about Henry's law. Concentration. Concentration. The stuff I jump over, you guys can just jump over it too. It's not critical. You can read about it in your book if you want. It's interesting, but I'm not going to touch on it. Okay. Concentration of solution. Now, there are a bunch of ways we can express concentration. The first most common way is percent. Expressing concentration in percent is probably the most common way we do it in society. There's 3 ways to express that. Percent mass over mass. Percent volume over volume. Percent mass over volume. And there's one more, and we call it molarity. molarity is moles of solute divided by liters of solution. Underline the word solution. If people often make that mistake. They'll divide by the liters of solvent, and that's not right. It's the liters of solutions. It's the total volume of solution. Okay? Now, here we have masses and masses, right? Volumes and volumes, masses and volumes. Here we have moles. Which one do you think chemists use most often?
The last one.
The one with moles, right? Well, we use these as well, but these are more common in chemistry. Now, in our society, medicine's no different. These are used quite often, right? We're going to talk about them too. Percent mass over mass is the mass of solute divided by the mass of solution. That's multiplied by 100. You've probably seen this formula before, haven't you? Like on the first exam?
Yeah.
It was on the formula sheet, wasn't it? So you don't have to memorize it. You're welcome.
Thank you.
Volume of solute divided by the volume of solution. Notice it's always the solution in the denominator. It's never the solvent. Solute on top, solution's always in the bottom. Mass over volume. Mass, solute. That's always in grams. Volume of solution. That's always in milliliters. Okay? These ones can be whatever you want. Kilograms, kilograms, grams, grams, milligrams, milligrams. As long as it's a mass unit on top and bottom. Here this could be milliliters, liters, whatever you want. As long as the same volume is on the top and on the bottom, you can do it. Okay? But you can't have milliliters and gallons. For example, that's the milliliters and milliliters. Grams and grams. That's the same. Here, it's grams and milliliters. Okay? Those are your formula for concentration. And all of those are on your formula sheet. Don't memorize. Some of you will just remember them, but you don't have to memorize them. Okay? All right. Let's just do a problem. Let's not even bother with preamble. Let's just jump into it, right? It's easy stuff. You guys have done harder math than me, I promise. All right. We're going to do this one together, Amy. Now, this is a multiple choice question. But one of those A, B, and C is correct. So let's do this together. A solution is prepared by mixing 15.0 grams of sodium carbonate and 235 grams of water. Calculate the mass percentage, M over M. All right. We've got to calculate this, mass over mass. Okay? Now, it doesn't say anywhere in there to calculate molarity, does it? No. Molarity means moles. We want this one. This doesn't mean moles. Are you with me? Common mistake people make here. Don't convert grams to moles. Don't do that. How do I know not to do it? The question clearly states it wants me to do a percent mass over mass. So I have to have a mass divided by another mass. I don't need moles. Okay? So don't convert to moles. Okay, here we go. Let's write some stuff down. We have mass of solute. What's the mass of the solute? 15 grams, right. 15.0 grams. It's always in there the lowest number, right? What's the solvent? Now, I know that this is the mass of the solvent because it tells me it's the mass of the water. Okay? It didn't say mass of solution. It didn't say total mass. It said mass of H2O, the solvent. Okay? So now, how do I get the total mass of solution? Yeah, you just add them up. Simply add them together. Total mass of solution is 250 grams. And I knew that this was the solvent, again, because the question said water. Okay, it didn't say mass of solution, it didn't say mass of, it didn't say total mass, it didn't say anything like that. It said gram of water. Okay, that's the solvent. This is kind of a little bit tricky because of that. Most times you won't see that, it doesn't happen like that. But this one is, so you have to be careful. You all right with that? Okay. So now, this is the mass of solution. Let's put that down. that is going to go here. And this is going to go there. Does that make sense to you guys? I think I'll multiply by 100. 15.0 grams divided by 250 decimal point grams. Multiply that by 100 equals. Rashida! Aha! I have these two bad boys together. This is mass. This is the mass of the solvent. This is the mass of the solute. You add them together, you get the total mass. Very good. What is it? 6.0? So C. Know what everybody else does? 6.00? All right, notice at the end here, I put percent M over M. The reason you do that is to tell the reader, whoever's looking at whatever solution you made, that you determine this percentage using masses. Okay, because there's also mass over volume, right? Be careful. Be really careful. Is that hard? Good, it's not supposed to be hard. Yes, let's not bother with that. Who is it? I had a question up here. I lost it. It's the last sucks. Okay, we'll make one up. I'll make a question up for him so I don't know where I went. I didn't save it. I guess I did not save it. All right, here's a question for you guys. Let's say you dissolve 183 grams of sodium chloride into water. The total mass of solution is 501 grams. Period. What is the mass over mass percent? There you go. It's not supposed to be hard. Who's done? One more minute, guys. How easy is this? No. I've never tricked, well, maybe I did. Not probably. What was on top? 83. Okay, that's it. Grams. Divided by what was the bottom? Aha! You don't add them together? Why not? Aha! And trick you guys. What's the final answer? Everybody else see 36.5? All right, very good. So they're not hard, right? I mean, they're not hard. Yeah, go ahead. Whenever it says gives you the mass of water or the mass of solvent, you gotta have it. If you give you the total mass or the mass of solution, then you don't have that. That's already given to you. Okay? All right, moving on, right? That's easy. Nothing to that. You guys are laughing at the simplicity of that problem, are you not? You want a whole exam of these, don't you?
Yes.
See? I knew you guys thought it was easy. Just one question, this one, and we all go home. If only we could get away with that.
That should be our final exam. That one.
Yeah, I would definitely get called into the principal's office for that. All right, molarity. Now, molarity is easy. It's just a little bit more involved than percent solution, but it's still easy. You have to convert to moles, exactly. That's it. And you have to make sure that your volumes are in liters. That's it. Okay? I know everyone in this room can convert milliliters to liters or liters to milliliters. I know you can do that. I know that's not hard. All you got to do is remember to convert to moles. So, molarity. Moles divided by liters. That's how it's written on your formula sheet. Okay? You have to remember it's moles of solute, liters of solution. Okay? You have to remember that. So, that's it. Now we want to do a problem. We're just going to work a problem. The best way to learn how to do molarity problems is work problems. Just do problems. Here, let's do this one together. What is the molarity of a 5.00 liter solution of sodium hydroxide if it contains 6 grams of sodium hydroxide? All right? First things first, it wants to know the molarity, right? You go to the formula sheet, you find the formula for molarity. It's capital M. Capital M equals moles over liters. We have to remember, it's liters of solution, moles of solute. Solute is always in the numerator. Solute, okay? So, we know that sodium hydroxide is what we're working with. And we know we have 6.00 grams of that stuff, right? We have to convert to moles. We also know the liters, right? Okay. So now I know that this thing is going to go here, right? Easy. But I try to put this in here, and I go, wait a minute, there's a unit mismatch here. We have grams to be moles, right? But that's okay, because you guys are highly skilled chemists, right? You know you can convert grams to moles if you have the molar mass, right? You guys all know the molehill, right? But I didn't give it to you. But I gave you the formula, didn't I?
Yeah.
So good for us. We can figure it out on our own. How do you figure out the molar mass of sodium hydroxide?
You add the mass of sodium.
There we go. And hydrogen, right. And the molar mass of sodium is 22.98. That's the mole multiplied by 1, of course. 16.00 grams per mole multiplied that by 1, of course. And that's going to be 1.01, right? Grams per mole. And add everybody up, yeah? 9, 9, 5, 3. Doesn't look right. What do they come mistake? Oh, 9, yeah, you're right. How did it 5? Good for me. 39.99 grams per mole. Okay, 40. 40. I've done screwed up somewhere. All right, let's carry through this. 39.99. Now, that's the molar mass, right? How do we convert grams to moles with the molar mass? easier than that. Much easier than that. We got here the molehill. Look at the molehill, right? Grams are here, moles are here, right? We want to go from here to here and avoid Fred. So what is the toll that we have to pay here? Grams per mole tax, right? So here's what I want you to say. How do we convert grams to mole? We use the units. We let the units tell us how to do it, right? Right?
Yes.
I think some of you who aren't using your units yet are having a hard time with this stuff because you're not letting the units tell you what to do. Every chemist that I know in the world, I know a lot of chemists, they don't know how to do these questions. They know how to let the moles tell them, not the moles, the units tell them how to do the question. The units dictate everything. Honestly, I don't know how to do this question, but I know how to use units. So I start with grams. I multiply by something that's going to give me moles, right? So I know that grams go on the bottom and the moles go on the top. How do I know that? The units will cancel, right? Same thing every time. Okay, what number goes here? 39.99. And 1 goes here. Comes down here, right? And 6.0 goes right here. So divide it through. I'm just going to do it for that. It may not be exactly that, because it's a little off. Whatever. It rounds up? Okay. Is that hard? Probably was because you didn't remember how to do it, right? You didn't practice it over the week? Okay, so now we have the moles, right? That goes in there. The hardest part of this question is remembering to convert the moles, and then remembering how to do it. And for my money, don't remember how to do it. Remember how to use the units. The units will tell you how to do it. You know, it's kind of like the Force in Star Wars. You surround it, you got it. All right, similarity, moles per liter. Similarity equals 0.150 moles. Remember, when you abbreviate, when you write the word mole, write the whole word, MOL, or you can take E off. That's the abbreviation for mole. Do not say M. Lowercase m is mass. Okay? 0.500 liters equals 0.3. There we go. 0.3 moles. Now you can write it like that, or you can say this unit or that unit is fine. Because capital M means that, right? Okay? Either one is fine. There's one for you. What is the molarity of 0.225 liters of a KNO3 solution containing 34.8 grams of KNO3? And I'll give you the stuff. I'll do it here. I tell you what. Come on over. I'll give it right back to you, I promise. I'll give you those masses of the elements up here. Remember on the exam, you'll get your own periodic table, so you don't remember everything. K equals 39.10 grams per mole. And 14.01 grams per mole. And O equals 16.00 grams per mole. All right. Work together. You don't have to work alone. love these questions, by the way. That's a whole bunch of things at once. Yep. I would call it a gram to mole conversion. I don't know if it has a special name. I just think it's a gram to mole conversion. That's all. Raise your hand if you're done. Nice. A few more minutes, guys. Those of you still working.
Yeah, I had this teacher. He was like, yeah, not a pronunciation. It was like he would say something and it wouldn't make sense.
I see a lot of things that don't make sense.
Oh yeah, it's just like.
I like that.
Oh, with like the oxidation, I had no idea what oxidation was for like a whole year. And I was like, what is that? He would say stuff, and I'm like, I don't understand. You had it in like 5 minutes.
Oh yeah. I kind of know the words to use. All right, guys, how are we all doing? You guys doing all right?
Yes.
Anyone want a little more time? All right. How much more time do you want? Hold on, just go. You guys come over there. You're on the right track. Keep going. Get the hard part now. Not the hard part. The rest is putting it together. All right, ladies and gentlemen, here we go. We have 0.225 liters of solution, right? That right there, SOL apostrophe M, that's how you abbreviate the word solution. So I'm just going to start using that now. That's okay. So that's how you abbreviate solution. Oh, goodness. Oh, yes, we have 34.8 grams of KNO3, potassium nitrate. There we go. Fertilizer. I do?
Oh, no, not you.
Oh, okay. All right, so want to know the molarity. And we have the volume already. Please do some question. Now be careful. On an exam, I'll probably be giving you the volumes in milliliters. Okay? Most people aren't going to say 0.225 liters. They're going to say 225 milliliters, right? This sounds better. So you have to remember to convert it to liters, right? The formula's on the exam, so you'll see the letter L written clearly. All right. We know the volume, but we don't know the moles. That seems to be a common theme in these questions. So, what we do know, KNO3. But we don't have the molar mass. Now be careful. On an exam, I may just give you the molar mass. Okay? It might be written there. How is it written? It would be written right here. So we're going to let KNO3 parentheses mm, molar mass, equals some number grams per mole. Okay? You don't have to cut this. So if you do, it's okay. It's not wrong. It's a time thing. You just always a lot of time doing it. If I give it to you, I may not. So keep that in mind. 1 times K, 1 times N, 3 times O. Right. Just got to pay attention. Now, what's the mass of potassium? I erased it.
39.10.
Grams per mole. Nitrogen was 14.1, wasn't it? 0.1. And this is going to be what? 48. Oh, and then you get something like 101, right?
And 0.11.
11 grams per mole. That's the molar mass, right? Did y'all get that? You may have rounded it wrong, but you get something like that. All right. Let's remember the molehill, yeah?
Yes.
Mole up here is what we need for this formula. And we're down here at grams, so we know we have to pay this tax. 101.11 grams per mole. You gotta pay that. Okay. So how are we going to convert grams per mole?
The conversion factor.
We're going to let the units tell us.
Let the units tell us.
Let the units tell us. Either are we starting with?
Grams.
Grams. Where are we going? So just by how we've been doing it the whole semester, what has to go here?
Grams.
Grams. What has to go here? Oh. That's how I know. Let the units tell me. I can never guess. If I guess, I'm going to guess wrong. 34.8 goes here. Number 1 goes there. And 101.11 goes there. Common question and a common mistake on these things is people will multiply here when they should have divided. And if you want to know what you're supposed to do, the units will tell you. Try to do it without the units. Good luck. All right, what's this number here?
0.344.
That's how many moles of potassium, potassium nitrate you have. And that's going to go here. Right? And that's going to go there. We divide the moles by the liters. Now this question is not hard. It's just involved, right? It's more than one step. It's actually 3 steps. Molarity equals 0.344 mole divided by 0.225 again, 5 liters equals 1.53? 5.3. Or 1.53 mole per liter. Either one's correct. They're both correct. Okay? But I can't hear you. Keep up. We do another one. I don't know if I have one. If I have one, we can. It's a similar question. Similar, not the same. You know what? This question here, you definitely got to use units.
Yeah.
You definitely got to use units. Do this one, try. You can do this one. You can do anything. Let your units tell you what to do. Don't guess. The units will tell you if you like them. If you don't like them, they won't tell you. Look at the molehill. It'll help you. But again, if you can do this one, you can do anything. Anything involving molarity, that is. A little harder, but you guys can do it. Allow the units to work for you. Let them do their job. Better calculate grams. Remember, molarity is moles over liter. Rashida! What is the mass of aluminum? 26.98. That's aluminum. Chlorine is 35.45. What? I see something. Yep. There's your moles right there. Moles per liter. If the units work, they will come down to it.
Oh, wow. Wow.
These units? did not know it.
These questions are in the book.
Similar ones, right?
Oh,
This one, back one, I don't know if it's in there or not.
The odd numbered question answers. Okay, I got C. Yeah, A. Right now, okay. Yeah. I did. I knew that. Made it 1.25. Yeah, no, yeah. Is the rarity, not the rarity. Rarity equals. Yeah, we usually half the grams first.
Who's got an answer?
Got an answer.
Just an answer. Doesn't have to be right or anything. Just comment. Who's letting the units tell them which way to go? Good. The units will tell you how to get there. You gotta trust them. This is a question you've never seen anything like this before. I know you haven't.
Yeah.
Guess what? Life's like that. There are lots of problems you've never seen before. But you have to think through them. Don't panic. Chill out. What are, well, you're gonna
Oh, the last step, yeah. the number you got from 0.125. I have seen this. Oh, here you go. I did one of this. Yeah.
All right, ladies and gentlemen. Tough question, huh?
Yeah.
Well, like every other question we've ever done, what are you starting with? What's the only unit you can start with? Well, we don't have liters, do we?
You have to convert.
We have milliliters, right?
Yeah.
We're going to start there.
Yeah.
We've never, ever started with a 2-unit conversion factor. We've always started with a 1-unit, haven't we?
Yeah.
We're going to start with the only unit we have that's by itself, that's milliliters. Don't know what we have. Start there. So we're going to convert milliliters to liters, right? And what's the goal here? The goal is to get on this molehill somehow. We have to either get moles or grams. One of them will get us on this hill. So which one can we get? We get moles. We get a conversion factor that has the word written in it, right? So we're going to have to use this conversion factor to get ourselves on this curve. We've got to use volume to do it, right? Because the conversion factor involves liters, yeah? I'm going to start with volume. So we got milliliters multiplied by sum, and get milliliters on the bottom, liters on the top. That'll get us out of milliliters into liters. And then I know, because I have the molarity, I can multiply like this. Liters, moles. The liters go away. Right? You what? Yeah, you did. That's why I couldn't understand what you're writing. That's why I just said maybe. All right. What number goes here? 1. What number goes up here? Is that the, not that? Right. How do I know it's that? Well, both up here, right? What number goes up here? Goes down here? What goes over here? 125 divided by 1,000 multiplied by that. That'll get you moles. And that'll get us on the table. Look at this up here. Okay? Anyone do anything like that? Anything similar to that?
I did something completely, like, I just looked at that equation and I put 1.150 equals moles over 0.125.
That'll get you there.
Yeah.
You have to say a number.
Yeah.
That'll get you there.
I was just looking at
It's another way of thinking about a problem, is using the formula to manipulate stuff around it.
Yeah.
I don't like that, because I don't know the formula I can do it.
Oh.
But you'll have it on your
That'll
exam.
be on the
You'll be all right.
exam.
You'll be okay. What's the number here?
What?
A.
Oh, well, I
So what everyone else got?
Oh.
Someone do that out for me, make sure that's right. I want to go on with
Well,
that.
that's it rounded.
Okay, that's rounded?
Yeah.
Rounded properly? Okay. So that's how many moles we have, right? So we can just, if you want, you can stick up here in the old mole hill, yeah? Now we gotta go from here down to here. We gotta do this first, though, don't we? You have to know how much to pay to drag it. So you calculate the molar mass is this, and you get, hold on, 0.88. That's total. That's the total the dragon requires. Now we got to convert moles to grams, right? How are you going to do that?
Let the units
Let
tell
the
you.
units tell you how to do it. Starting with moles, right? So multiply by something to give us grams. What was in the bottom? What was in the top?
Grams.
So now we know. What number goes in the bottom here?
1.
What goes up here?
1, 2, 3,
What goes over here?
4.
Multiply through. What is it?
50. Yeah, it rounds up.
25 grams. Okay? Hard question? Tough question. Well, not something you should be able to do, really. You should be able to figure it out. What I would do if I were y'all, and maybe, maybe you might want to listen to me, is I would cover up my answer, and I would do the question again at home tonight. Make sure you can do it. Because if you can do this question, you can do any of the other questions I've asked you, because those are a lot easier than this. Okay? Don't you think? Okay? Make sure you can do it. Dilution of solutions. Write the title down for me, please. All right. Dilution of solution. Write the title down. Now, you guys all done this before. You all have done laundry before, haven't you? Ever put bleach in your laundry?
Yeah.
No, it depends. Those depend on how old your washing machine is. You have a newer one, it kind of does it for you. You have an old school one, you got to be careful. You can't just throw your clothes in the washer and add a bunch of bleach. Okay? That ain't going to work. You're going to get a bunch of bleach stained clothes, right? You got a new wash, you put in a little compartment and the machine injects it for you. Right? But if you're old school like me and cheap, buy the cheap washing machine, yeah, you have to add the water to the clothes washer first, right?
Oh yeah, you let the water run.
You let the water run first before you put any clothes in there, right?
Yeah.
Yeah.
And then you add the bleach, right?
Yeah.
So you stick your hand in there and you whirl it around, right? That's how we do it, right? And then you throw your stuff in there. Why do you do it that way? To dilute the bleach, right? So the bleach is not so strong. So it won't stain your towels and your delicate whites, right? It will just make them cleaner. Yeah, me too. We all learned the hard way. We all learned the hard way on that. Okay, so that's a dilution. You took the bleach from a concentrated solution of bleach to a dilute solution of bleach. Okay? That's, you've all done dilutions before. Or, if we're in Florida, you probably all dealt with concentrated orange juice. Ever drink that stuff? Don't even bother. For me. Drink the fresh stuff. It's better. Well, that's another story. Now, you buy a frozen concentrated orange juice. You go to the freezer aisle. It's literally a tube of orange juice concentrate. The orange juice concentrate is orange juice with the water and flavor essentially removed. Okay? So when you drink it, you can't just drink it from the can. If you could, it will burn your mouth. You have to add water to it, right? Okay? So you take a can of frozen concentrated orange juice, here they thaw it out, pour it into a pitcher, and you add 3 parts water back. Okay? You take that same can, fill it up 3 times, and add that water to the pitcher. This is a dilution. Now let me ask you a quick question. This is about 100 milliliters of orange juice concentrate. Okay? We added 300 milliliters of water to that. But even once you've added the water, there's still 100 milliliters of the orange juice concentrate, right? It's just spread over a bigger volume, right? So the orange juice molecules that were here are the orange juice molecules that are here. There's not any more of them, not any less of them. There's just more solvent, right? When you do a dilution, you literally add solvent. Make sense? Yeah. Solvent. This is the washing machine, right? You fill it up with 50 gallons of water, pour a couple of bleach in there. You went from a cup of bleach to 50 gallons of bleach. Well, the same number of bleach molecules that were in that cup are in that 50 gallons of water that are spread out. Okay? That's why they don't stain your clothes. Well, you're not supposed to wash your colors in bleach anyway, right?
Yeah.
But you wash your towels in bleach, people. Not every day, but at least once a week. So we'll talk about it. Okay, never mind. I thought it was fine. All right, solution. Here you go. Water is added. In other words, solvent is added. Solvent is added. The volume of the solution will by necessity increase, and the concentration will decrease. Remember, concentration is the ratio of solute to solvent. Solution volume. back to my doping one on that. Now, concentration will by necessity decrease. Volume goes up, concentration goes down. The inverse is proportional. One goes up, the other goes down. One goes down, the other goes up. Okay? But the mass of the solute never changes. So if there's 100 grams of solute here, there's literally 100 grams in there dissolved in the bigger volume. Okay? That's all dilution is. You're just decreasing the concentration by adding solvent.
So it's more very just another word for concentration.
It's the ratio of the moles per the liter of the solution. So, here's a formula you may have seen on the formula. Oops, that's C1, C1. You may have seen on the old formula sheet. C1, V1 is C2, V2. You may have seen that, not know what it was. Easy. C1 is the concentration. Right. It also is written sometimes CI, CF, DF. Sometimes it's written that way.
Yeah.
I write it this way. Sometimes you'll see it that way. CI stands for initial concentration. VI is initial volume. CF, final concentration. VF, final volume. Same thing up here. First concentration, second concentration. First volume, second volume. Now, when we do questions with this stuff, the hardest thing to remember is what number goes where. That's what everyone always panics about that. It's easy. It's easy. Remember, when you do a dilution, the concentration always goes down. When you do a dilution, the concentration goes down. And the volume of the solution goes up. When you do a dilution, you're adding solvent, right? You're not adding solute. Is that clear enough? You know what's next, right? What volume of a 2% mass over volume hydrogen chloride solution can be prepared by diluting 25 milliliters of a 14% solution? All right? Easy enough. Here's how we approach it. First of all, you recognize this is a dilution problem. It's a dilution problem, right? So rate the question, diluting. You're going to go to the formula sheet. You're going to find C1, V1, and C2, V2. You're going to breathe a sigh of relief. Now we're going to figure out what's C1, what's V1, what's C2, and what's V2. Well, first things first. What's the question asking us to figure out? What volume of a 2% solution? Okay, so that's one of my concentrations, 2%. Remember, percentages are also concentrations, right? And we have a 14% solution. Well, when you do a dilution, does the concentration go up or down?
Down.
Down. So which one of those numbers is bigger? The 14 is larger, right? So it must be C1. C1 has to be bigger than C2. Because when they do a dilution, the concentration goes down. This is 14.0 right here. Right? Yeah, 14. Yeah, 14%. And C2, I'm sorry, yeah, I was right. Sorry. 2.00. Now that's one way to do it. The other way is to read the question very carefully. Just be very careful. Read what it says. What volume of the 2% solution of HCl can be prepared by diluting this? So it's telling you that everything after that word is C1 and V1. It's telling you that. You read it carefully, that's what it's saying. Right? So this must be 25.0 liters. And this is what we're trying to figure out. Remember, concentration goes, volume goes up, concentration by necessity must go down.
On the slide, it's 5.0 milliliters.
Oh, that's what meters? Oh, sorry. There you go. I'll just read that. All right, now, before we do anything, we're going to think about logic. If the concentration went down, this number here should be bigger or smaller than this number here.
Bigger.
This number is bigger. This one or that one? This one should be huge, right?
Yeah.
Compared to that one, this one should be much bigger. Because we're diluting, we're adding salt, right? All right, very good. So, C1V1 equals C2V2. This is what we're trying to figure out. Now, these kind of questions are rare for me. One of the few times I'm not going to let the units tell me what to do. I'm going to use the formula. I think it's the easiest. Okay? I know I have to solve for V2. So I'm going to do a little bit of algebra. Divide both sides by V2. Now, I'm going to do this algebra, but I'm not going to ignore the units. If you ignore the units, you do it at your own peril. That means V2 equals C1 V1 over C2 equals. Now, I'm going to put some numbers in now, but you're going to notice I'm going to carefully put my units in as well, because I want to make sure I'm right at the end. When I do this calculation, I had better end up with milliliters. That better be my final volume, or my final unit, right? If it's not, I've made a terrible mistake. I better go find it. Okay? So, that's going to be C1, which is 14%. V1, which is 25.0 milliliters. We're going to divide that by C2, which is 2%. Percentages cancel, leaving me in a unit per volume. That's good. I also remember this number we're calculating has got to be bigger than 25.0. If it's not, it's probably wrong. You got to check it. What's my number here? 175? So there's two checks I've done. My unit is correct. It cancels properly. The number is bigger than what I started with. So I have high confidence that that number is right. Does that make sense? Easy, right?
Do I need to
No. Nope. Just use them exactly the way you're given. Right. So how was that? Was that fun or what?
Yeah.
All right, listen up. Listen carefully, please. Please listen to me. I'm about to give you an announcement of something important. Veterans Day is coming up. There is no class on Veterans Day, November 10th. So I will not be here. However, the school is still open for whatever reason. The offices are still open. So if you have any business to do with the college, probably doing it on Veterans Day would not be a bad idea. There won't be anybody here, unless of course you go to a memorial. The quizzes are right there. Please pick it up.
So it is on the 17th, the exam.
I don't know.
Yes,
I got some syllabus? Okay, that's what it'll be.
So we got class, no class.
Don't be offended, but I don't recognize. Oh, okay. All right. I didn't recognize you. I mean, I don't care. I don't recognize you. All right. So you're supposed to be here. All right. Very good. Sorry. No, you're usually here on time. Yeah, that's fine. All right. Thanks for having me. All right. Nice to meet you. Sorry I didn't recognize you. Oh. What's up, man? Goodbye, Internet.
Thursday gonna be too late.